Hi guys, can I get a sound check?
Yeah, we can hear you.
Okay, great, thanks. All right. Sorry guys, I'm trying to get my act together here. All right, guys. So, today it's going to be our first day, sort of getting past the diodes into transistors. And the first set of transistors that we're going to be talking about are going to be bipolar transistors. So, I may have talked to you guys about this, but if I did, it doesn't hurt to go over it again. So far we have been talking about diodes, and these are semiconductors made of a P and an N junction. So these two things are the same, and they're used in a variety of applications. They're used in, we looked at voltage regulators, like LEDs, limiters, things like that. Okay, so you see diodes a lot. They're like sprinkled all over semiconductors everywhere, and that they are used specifically in circuits. But what you'll probably mostly be working with when you work with microelectronics and semiconductors are going to be transistors. And so what's the difference between diodes and transistors? So diodes have two terminals, and transistors have three terminals. They're both semiconductor types. So a two-terminal device just means, there's two connections to something that has a certain function. So there's, whatever, x and y is equal to f sub x. Just means two connections to it, like a diode. You have two connections. So a three-terminal device has three terminals. So you'll have, typically what that means is you'll have some kind of a control input, and then some kind of an output, and then some kind of an input, or maybe there's a reference, something like that. But there's actually three connections into a transistor. And you can do, sorry, Jonathan, let me see, you got a text. Or download. Oh yeah, are you guys able to see slide deck 6?
No, could you unpublish or publish it?
Oh,
sorry.
Unpublished. Sorry about that, guys. Where are we? Modules. Slide deck. Yeah, unpublished. Sorry about that. Can you guys see it now? It's in a module called Bipolar Transistors.
Yes, there now.
Okay, great. I'll give you guys, sorry, I'll pause here for a second. You guys download it. By the way, of course, these books are real. What are you guys talking about? Hologram. Let's see. Oh, one up. Real books. I haven't read all of them, but they're real. All right. Okay, guys. So let's keep going. So three terminals in transistors, and you can do a lot more with them than with diodes. So, why is that? I think the main thing is that there's three terminals, there's more flexibility, but, one of the main things that you get out of a transistor, it's not the only thing, but it's one of the main things that they're known for. And so we'll be focusing on quite a bit is something called using them and basically as a gain element. Oops. Gain. So that's what the actual functionality of it is. But when you have a circuit that gives you gain, you also call it an amplifier. Okay, so that's one of the main things. So let's, for example, look at and you use those a lot in circuits. It turns out, a lot of the things you see are really amplifiers used in different configurations. Now, what confused me, again, I'm trying to keep going back to work when I was, taking a class like you guys were many years ago, was, I could see, well, you need to have, you have a small signal in some points in your circuit. So I could see advantage of increasing the amplitude of that to get amplification, to get gain. But that seems like, well, is that everything we're doing in electronics? Does it seems kind of like, sounds not like a very flexible thing. It's just taking something small on the input, but amplifying it on the output, increasing the amplitude and putting it on the output. But it turns out once you have gain, you can build a lot of other functionality based on having this gain. And it's a little hard to describe, the sort of the delve into the deep aspects of it, but mainly it comes from having feedback circuits. And I don't know if you guys have looked at feedback or will be looking at feedback circuits, etc. But once you have this ability to have gain in a circuit block, you can put it into various circuit configurations and get a whole lot of different functionality from it. But let's look at just, sort of a simple path. Let's look at a cell phone at the block level. So what you have on the transmit side is you have like a microphone. So a microphone. So a microphone is something that takes pressure, so air pressure essentially, and translates it into an electronic signal. So it takes air pressure, which is me talking or whatever, you guys talking into your cell phone, and then gives you a voltage out on the output, but it's a very small voltage on the output. So the first thing you'd want to do is to increase the amplitude of that small voltage. Why do you want to increase the amplitude? Is because in all systems, all electronic systems, there's something called noise, which is a very important concept. Noise is basically a signal that you don't want. And so this is a electronic definition of noise, electrical engineering definition of noise. It's not an everyday definition of noise. It doesn't actually have something to do only with an audio signal. So you can have noise in video signals, you can have really noise in digital signals, etc. But you can certainly, it's easy to, you've all heard it when it's in the audio signal, like, if you don't have any audio playing and you just turn the gain up on your headphones or something like that, you kind of hear this hiss, depending on the quality of the system you have, etc. And that hiss is like this noise, this unwanted signal that, excuse me, comes from just all sorts of places. Unfortunately, there's a lot of places that generate noise, but you basically get this noise injecting itself in all sorts of places in your system. And a lot of noise is additive, means that it's, if you have a signal level, you'll get, the noise adding to it. But then if you have, say, 10 times the signal level, and you get the same noise, that means your signal to noise ratio means the quality of your signal, the amount that your wanted signal is higher than your noise value, then your unwanted signal is much higher than your signal is larger typically. So that's sort of this first stage of amplification, is you're just increasing that signal from your microphone just to make it less susceptible to noise. Another thing about audio signals is they're pretty low bandwidth. So, you're talking about audio or your voice, it's maybe between, signal coming out of the microphone is maybe in the 10 to 20 kilohertz range in terms of frequency. And so you're just amplifying that. But it turns out that you can't just, remember, this is a cell phone. So I'm talking into a microphone and I want to transmit that signal to, a base station. Now it turns out it's not easy to transmit signals that are only 10 to 20 kilohertz. Why is that? Well, again, you'll see this in other classes, but to get a antenna to work well, it needs to be sort of a good fraction of so basically what happens is frequency and wavelength are sort of inversely proportional. So something that has the low frequency has a very long wavelength. And antennas need to be, typical sort of sizes for antennas is you want to make them about 1/4 the wavelength of the signal you're transmitting. All that upshot of all that is if you try to transmit something like your audio 10 to 20 kilohertz signal directly, you need like an antenna the size of, like a football field or something, like a very big antenna, because the antenna again is proportional to the wavelength, and the wavelength is inversely proportional to your signal frequency. So what you want to do is you'd like to, so when you have something the size of a cell phone and you have an antenna, I don't know, the antenna on a cell phone might be in, several centimeters, let's say 10 centimeters or something like that. That wants to have something signal with a frequency of several gigahertz. So like 1 to 2 gigahertz. That's why, cell phone signals are, 1 to 2 gigahertz signals, or, your Wi-Fi signals at home are 2.5 gigahertz or 5 gigahertz, depending on if you have 5G or whatever. So so one of the first things you do after you've amplified your audio is you mix it. There's this process called mixing with a 1 to 2 gigahertz oscillator. 1 to 2 gigahertz reference value. So you need a oscillator to generate 1 to 2 gigahertz worth of signal, and you need to want to mix it with your amplitude. And what you get then is you get the signal sitting on top of a carrier, and now you can put it into a reasonably sized antenna that would fit on your cell phone. Now you're sending out 1 to 2 gigahertz wavelength signals, antennas. So it turns out that besides just the amplifier, like for example, this mixing has gain elements in it. This oscillator has gain elements in it. One thing I forgot to draw here is you need a very high output power to drive the antenna, because the cell phone tower might be very far from you, from your cell phone, and you want to have a lot of output power. So that the power amplifier also has amplification. So everything along here has gain elements built in, whether we're actually using them as amplifiers or not. And then when you look at the receiver signal on your cell phone, it's similar path. So you'll have an antenna on your cell phone. It's the same antenna, but I'll just draw it as was separate. And that's also receiving at this point a very small signal, because you might be very far from the cell phone tower. So the signal is very weak coming into your cell phone. So you'd like to amplify that using a low noise amplifier. These are like very specific names because they mean something, and we're not really going to go into it in this class, but very specific type of amplifiers. So you'd like to sort of have another oscillator, and you want to convert the bandwidth. Then you want to put that into an analog to digital converter. And then this goes into your digital signal processing and goes into your cell phone, the rest of your cell phone. So again, all these circuit elements, a low noise amplifier, mix, oscillator, analog to digital converter, all these things have gain elements. So when you look at your, just your cell phone, both the transmit and receive path have a bunch of like lots and lots of gain elements. I don't know how to emphasize this enough, but they're not just doing amplifications, but you need the gain element to build other functions. Okay. So let's just look at what does gain mean typically. So there's different types of gains. There's like current gain, there is current to voltage gain, there's voltage to current gain. But most amplifiers and almost the entire range of what we'll talk about in this class are voltage amplifiers. And basically, you have, what that means is you have an input signal, you have an input output signal, and you have a certain amount of gain. Let's say, for example, this gain is 2, a gain of 2. So, and let's say if I draw my input signal as a function of time, let's say my input signal does something, let's say it's a sine wave for the sake of discussion. My output signal is just going to be 2 times that if I had a gain of 2. There's a lot of other things, second order effects and stuff like that, but this is kind of what it would look like. It's basically taking that signal, and so this would be V out, and this would be V in. Okay, or alternatively, let's say Vn was not a sine wave signal, let's say it was, so this is voltage. Let's say Vn did, a bunch of weird activities. I don't know. So V out would just be, multiplying the Vn by a factor of 2, and every one of these interesting. Something like that, I guess. Like that. So basically, you're just multiplying Vn by 2. If my gain is 2, or generally A, can be anything. So it could be gain, I don't know, 1, 2, 10, you name it. Now, typical depends on, I guess there's not really any typical values, but if you're building an if you guys are familiar with operational amplifiers, these are amps that you put in feedback circuits. The gain here might be like 1 million, might be a huge gain. Or, if you're talking about I don't know, like a low noise amplifier, the gain might be 10 to 100 or something. If you're talking about a single stage amp, the gain might be a 10 to 100. So it depends. It really is all over the place. But the upshot, so this A value can be anything, but basically you're taking the input, multiplying it by this gain, and that becomes your output. Now, it turns out that a lot of times, because of the nature of, I don't really, philosophically, I don't know why, but I guess it's the way as you'll see, the way the transistors work that create this gain. A lot of time, gain is negative. So this tends to throw a lot of people off. So a lot of times, I mean, most of the time, what things look like is this gain is actually like -2, or it's -1 million. That doesn't mean, you'll be 1 million times less or 2 times less the output. It just means the sign is inverted. So let's redraw that again, the case where you have negative gain, which again is most of the time. So if I draw time, voltage, And now I draw my input sine wave. With a negative input, it just means, the amplitude of the output, it's still 2x the amplitude of the input, but the sign is inverted. Okay, so if the input's going positive, the output's going negative, and vice versa. And so circuit designer, so this is different than attenuation. Okay, attenuation would be, so this is very different than attenuation. Attenuation would be like a gain of less than 1. So if, let's say, your gain was 0.2, then your input, if your input was, this much, your output would be like that much. So you're actually making the signal smaller. But so just because your sign is negative doesn't mean you're making the output smaller. It's just saying that you're making the polarity of your output the opposite as the polarity of your input. And like I said, this is the majority of the cases, and we're going to immediately see that the gains we'll be talking about are negative, but it doesn't mean attenuation. It just means that there's a sign flip from the input to the output. And circuit designers, everybody's really familiar with that, and they basically sort of we build that into our systems. Okay. Any questions so far about like the meaning of gain or what any of these things, attenuation, negative gain values, anything like that before we jump in? Okay, so let's keep going. Let's see. So let's see what is a one way to get gain? Well, it turns out that a transistor is acts like a voltage controlled current source. And so I'll talk about that and how you can get gain out of a voltage dependent current source first, before we talk about how a transistor maps into a voltage dependent current source. So in this slide, we're just talking about, let's say if we had a voltage dependent current source, what would it do? What it would look like. So let's first talk about a current source. Let's say you had a current source. So you put a voltage across this current source. Sorry, yes, looks really bad. So a current source has kind of there's an arrow driven across it. So let's say you put a voltage source across a current source. So the current source has the property that no matter what the voltage does across its two terminals, it'll have a constant current. So let's say this had a constant current of I1. So no matter what I do, no matter what this voltage does, it can go up and down, whatever it wants to do, the current will always be I sub 1. Okay, it's a current source, doesn't care what the voltage is across it, it's always outputting the same current. So that's a current source, the definition of a current source. A voltage controlled current source So K, V1. So the current here is KV1. Okay, and then I'm going to put a voltage source across it. So that's what should we call that? I'll call that V sub X. And then there's another voltage source, V sub 1, that's sitting somewhere else. It's not really connected to this current source. But notice that the current through the current source is dependent on this V sub 1. Okay, so this K value, so K has units of 1 over R. Okay, so K has units of 1 over ohm somehow. This case, K is some function, some constant multiplied by V1, which is sitting out unconnected to the current source I1, and like it's just sitting there. Okay, so now what happens? Still, if I draw this across V sub X, I would get KV sub 1. Okay, so let's say it has a certain current, right? That gives me a certain current. So let's say KV1. How should I put this so I wasn't confused, you guys? Depending on the value of V1. So let's say V1 is equal to 1. Okay, you'll get a current of, so I sub X, you'll get a current of K, right? K times V sub 1 is 1, so a current will be K. Now let's say V sub 1 is V sub 1 is 0.5, so the current ends up being 0.5 K. Let's say V sub 1, let's say for the sake of V sub 1 is a sinusoid with amplitude 1, you would get, the current would look like a sinusoid. Okay, with value V sub 1. So, but it's a voltage dependent current source, KV sub 1, but it's not dependent on the voltage across it. It's dependent on some other voltage sitting somewhere else. So for example, here it's really drawing the same thing. So I could put a voltage source here, for example, but this current source wouldn't care, this voltage dependent current source. This voltage dependent current source is just looking at this other whatever is in this other voltage. So for example, in this case, you have, if you put a voltage source across V sub 1, so I'm putting a voltage source here, so now got this guy, and then I put a resistor here, what would happen? So let's look at that case, right? So assuming I get this thing, my V out is equal to I1 minus I sub 1, because notice the current, the I1 is going this way. So it's going to be, the current's going to be going like that. So we're looking at minus I sub 1 times R sub L, right? The current, there's a V out, there's no other current except this guy. And so this guy is pulling current up from the resistor R sub L. So I get this negative I sub 1 times R sub L is the current here. Okay, and then I can substitute this KV sub 1 for I1. Okay, and then V sub 1 is the same as V in, because I put a voltage source V in across V sub 1. So I get V out is minus K R sub L V in. And then if I get the, so now if I put V in on this side, which is so ratio V out to V in, is minus K R sub L. Now, if you look at up here, where we said generally here, what we're saying is V out is equal to A times Vn. So the gain is, you can define the gain in as V out over Vn if you write it like that, the gain of this amplifier. So if we use the same definition here, when we have this ratio of V out to Vn, this is the same as gain of our circuit. Same as the gain of this guy. So the gain of this guy is this function of your voltage dependent current source times this resistance R sub L. Okay, so that becomes the gain of that circuit. So what does that mean? Well, again, if your input is a sine wave, so this is time, this is voltage. If your input is a sine wave with a peak voltage of Vp, your output, because your gain is minus Kr sub L, your output is going to have the inverted polarity from the Vn. So when Vn's going positive, V out's going negative. And it'll have some gain Kr sub L. Okay, so like K is a constant and R sub L is a constant. So this will make some amplitude. Remember, K has units of 1 over ohm. So K times RL, so K times R sub L is unitless. So it's just a value. So V out would just be some value times Vp, which is the peak value of Vn. Okay, as long as K times RL, as long as the absolute value is greater than 1, then the signal is an amplifier. So I want to put this absolute value signal here, because again, if KRL is a negative value, it's okay. You're still going to get amplification. It just changes the sign. And then when RL, the absolute value, is less than 1, is when you're going to get attenuation. Okay, any questions, guys, so far? So this is what would happen if you had a voltage dependent current source. Anything about that? So this is just like if I had this mystery circuit, somebody gave it to me, it was a voltage dependent current source, I can make a gain circuit out of this, a gain function out of this. Okay, and the reason we're talking about this is it turns out that a transistor can be modeled as something like this. Okay, more complicated version of this. So a transistor can be modeled as so that's why we're talking about this particular implementation of building a gain circuit, because that's kind of at the very first level what a transistor looks like. Okay. All right. Any questions about that? Okay. If not, let's talk about kind of what our transistor really looks like. So a bipolar transistor looks like a voltage control. So this looks like a bipolar transistor model. And we'll talk about what this bipolar transistor is and how you build it and how it works, etc. But it basically, you can model it again to the first level. It gets more and more complicated as you try to build a better model. But to first order, it looks like just a voltage dependent current source. So you have a certain voltage V input voltage, and then you have a certain current output. Now, the difference between what we're drawing here and the circuit that we had before is it's acting, a bipolar transistor is an exponential voltage dependent current source. So it's not just K times V1, but it's this function, exponential of V1 over V sub t. Okay, so it has a much stronger dependence of the output on the input than just multiplying a constant by V1. And VT is still our old, the old guy that we were using in diode, which is around 26 millivolts at room temperature. And all this stuff is like familiar from the diode days. It looks like the diode equation in forward active region. And in fact, that was one of the reasons why we started with diodes, is because a lot of those similar concepts, a transistor isn't exactly a diode, but some of those same concepts sort of apply. Okay, so let's look at, so that's what, so if we had this, I mean, we have it in a bipolar transistor, basically I can get gain out of this if I put a resistor here and get that V out. And then, so V out would be this current times minus this current times R sub L. So it'd have an exponential gain from V1, which is kind of a really nice thing, because the larger this number means that the higher the gain I can get out of the higher the gain I can get out of a circuit like this. Okay. Let's see. So any questions, guys, so far? Okay, so what does the bipolar transistor looks like? Remember, or the previous circuit we were talking about was a PN junction, the diode. So if I drew it, so it's a PN piece of silicon. So the bipolar transistor basically puts another N on the other side of the P. So you end up with a NPN. So it almost looks like having two diodes back to back. Okay, so this would be the P. So you'd have NPN. NPN is what the device would look like. And you'd have inputs to each one of these points. And so you have a 3-terminal device. So this guy is just this guy flipped on its side. So you have an NPN region. So again, and if you just had an NP, it would look like a diode. But we have an NPN, and we can make connections to each one of these regions. So it can get a connection to the P, connection to the N, connection into the top N. Now, one thing, it's tempting to see the bipolar transistor as just two back-to-back diodes, but you can only take that analogy so far. You know, it's kind of good as a starting point to think about it like this, but in fact, because of that, for various reasons, because this region is very thin, this junction and this junction are interacting with each other. So you can't just take two individual diodes and connect them back to back and get a transistor out of it. That's not how this works. That's where the analogy falls apart. These two junctions are communicating heavily with each other, and that's how you get the transistor action. So we'll talk about that, but just a warning that you know, this don't, if you try to analyze it as two back-to-back diodes, a transistor, it's not, doesn't work. And maybe in some operating regions you can kind of think of it like that, but not really. So don't take this too far. Just sort of trying to get you guys to see how this kind of evolves from a diode, the structure of it. And so it turns out that, so now notice this is, we're talking, went from a diode. So here's the, you know, the schematic thing for a diode, and it's a two-terminal device, meaning that there's two connections only to this diode. A transistor, because we're connecting to each one of these points, is a three-terminal device. So here's a symbol, just like this diode symbol is a schematic symbol for the PN junction. This symbol is the schematic symbol for a bipolar transistor. Okay, and so by convention, just like we had cathode and anode for the connections for the diode, for the bipolar transistor, basically this P region is always called the base. One of the N regions in the one with the higher voltage is called the collector, and the other N region is called the emitter. Now, a bipolar transistor is not symmetric, means that this N region is doped differently than the top N region. And you'll see in a few minutes why that's the case. But basically this thing is, you know, remember that we get an N region by having a lot of donor dopants in the material. This will be doped a lot higher than this collector region for this thing to work appropriately. Okay, so it's not like you can flip this. This is like drawn like it's symmetric, that you can just flip it upside down and still get an NPN, but it doesn't work that way. The emitter is very different than the collector. Okay, what else do I want to say? So the other thing is that you can also get there's another type of bipolar transistor. So this is one type of bipolar transistor. It's called the NPN bipolar transistor. There's another type of bipolar transistor we'll talk about a little bit after we talk about NPN, which is called the PNP. It's exactly that, so very similar, but you basically have two P regions surrounding an N region compared to the NPN bipolar transistor. And it also, you know, has, now here the N is called the base, the P is called the collector, and this P is called the emitter. And in lots of ways, it's sort of working exactly the opposite of an NPN. And so they, in some circuits, they tend to, in a lot of circuits, they tend to complement each other. But most of the transistors, bipolar transistors you see are NPN. And so we're gonna work through that. And then once we have a good understanding of that, we'll talk a little bit about the PNP. Okay, so let's talk about this schematic a little bit, schematic representation. So the way, so, basically looks like this. I don't know how to describe this guy. This point is always the base. The emitter is always the thing with the arrow on it. So a PMP sort of looks similar, but the arrow points into the device as opposed to coming out of the emitter. The arrow is still on the emitter, but it's pointing into this hat or whatever you want. I don't know what I would call this. And so, but anyway, for the NPN, this is what it looks like. This is the base connection, collector, emitter. And we have three terminals. So what this means is there are three voltages that we need to be concerned about. There's a difference, so that there's a voltage between the base and the emitter, and shorthand we call that VBE. There is the voltage between the base and the collector. Shorthand we call that VCB. So basically it's like the voltage between the collector and the base. That's saying the polarity. So for VCB to have a positive voltage means the collector has to be higher than the base. And then there's the voltage between the collector and the emitter. Okay, so now notice VCB, let's see, VCB minus VBE will give you VCE, but it's useful to have VCE as well. Okay, so those are the sort of shorthand notation for these voltages, because we'll be talking about these voltages over and over again. Okay. What else do I want to say about this? Nothing more about that. Okay, so now let's talk about how this thing works. So remember, a PN junction has, basically you've got this depletion region here. This is going back to our, it's called a depletion region. And so this depletion region has this built-in electric field caused by these non-mobile ions on the N side, and the minus non-mobile ions, stationary ions, on the P side. So there's an electric field pointing this way. So if you somehow manage to inject an electron directly into this depletion region area, what that electron is going to do is the electric field is going to push that electron into the N side, because the electric field is pointing that way. The electron is negatively charged, so the electron is going to get pushed into the N side. Okay, this electric field is keeping the positive charges, the holes in the P region, back, and keeping them on their side, and keeping the electrons in the N region on their side. But again, if you just somehow manage to throw in an electron in this depletion region, that guy would get swept into the N side. Okay, so this is an important property, and we'll see like how this works. So we'll talk about one of the main or the most useful operating regions of the bipolar transistor is called the forward active region. Okay, so what does that mean? So you have these three nodes. So you have the collector, this guy's the emitter, This guy is the base. This forward active region is when you forward bias the base emitter junction. So in this case, the emitter is connected to ground or 0 voltage. Okay. And then the base emitter voltage is 0.8 volts. Remember, our typical on voltage for a diode is around 0.8 volts. So basically this putting 0.8 volts here means that you're forward biasing this base emitter voltage. Okay. And then when you connect a higher voltage here, so let's say my collector emitter voltage is 1 volt. This guy is 0.8 volts. So it means that the collector is higher than the base by 0.2 volts. So VCB is equal to 0.2 volts. So it's just 1 volt minus 0.8 volts will give me a collector base voltage of 0.2 volts. So this means that collector base junction is reverse biased. And this means that the base emitter junction is forward biased. Okay, so this is just a, so I'm defining this up. This is called the forward active region, just this biasing, just this hookup of the bipolar transistor. And this is like the most useful, you could again, you can imagine doing lots of weird stuff with, you have 3 voltages to deal with. So you could hook it up in other ways, but this is the most useful way to connect it up. And that's what we're going to be talking about. Now, again, the slide is saying this is not the way to look at how this transistor will actually work. Don't think of it as 2 back-to-back diodes, because the transistor, the 2 junctions, the collector base junction and the base emitter junction, are interacting with each other in a really important way. So you can't think of it like this. Just you got to just think of it like this guy. There are 2 PN junctions, but again, the PN junctions are working together, working with each other. Okay, so let's see how this actually works. Okay, let's see. Did I put in a shoot? Oh, I thought I added a slide here. Okay, so before I talk to that, I thought I'd inserted another slide in here, but let me remind you guys of, if you had of the PN junction current. So let's say I had a PN junction. So, and then let's say I had a certain voltage here, N was lower than P by a certain amount, V sub F. Okay, so what would happen would be that we would the currents between we have a, if this is forward biased, we would have a diffusion current. Remember, we have a bunch of on the N side, we have a bunch of electrons. And on the P side, we have a bunch of holes that have positive charges. And then we have this depletion region. So when we put a forward bias on this junction, means we're allowing diffusion current. So we're allowing some of these electrons to go over here where there aren't a lot of electrons. And we're allowing holes to go from here to here where, you know, there's much more holes here than here. So by reducing this electric field in the depletion region, we are allowing a diffusion current to flow. And so, you know, the thing we didn't talk a lot about, I mean, we have worked out the individual currents for the diffusion current, but we didn't talk about how, you know, the relative doping concentrations here would affect it. It was sort of just implied, but let's look at the equation. So I think it's equation, yes, I wrote it down here. Okay, so. Okay, so it's, and I'm repeating equation 2.97 from the book, from the text. So the total current that's caused by this forward voltage is N sub A over exponential of V0 over VT. So that's the built-in potential times exponential of V sub F over VT. So this is V sub F minus 1. So plus N sub D over exponential of V0 over V sub T exponential of V sub F over V sub T minus 1. Okay, so this is the total diffusion current flowing. So one of them is the diffusion current of the holes, and it's this guy. And, you know, we have this term, the number, the doping concentration of the acceptors on the P side. So the doping concentration on the P side of acceptors. And this one is the current of electrons. So that's got the doping concentration of the donors on the N side. So you could think about this as this is kind of the, what is it, minus plus. This is the electron current. And this is the hole current. So, you know, that's the sum total of the currents. Now, nothing says that NA has to be equal to ND, meaning that, let's say the doping concentration on the N side, let's say it's 10 times higher than doping concentration than the doping concentration of acceptors on the P side, means that in this total current, there'll be 10 times more electron current than there is hole current. Okay, because it's dependent on the doping concentration on each side, or you know, it could be 100 times if N sub D is 100 times higher concentration than N sub A, or 1,000 times. It just depends on the different relative value of the different concentrations. Okay. Sorry, Brandon, I just saw your chat. Let's get back to that at the end of the class, because we're sort of off in another direction. All right. So anyway, so to continue with this, just so here are the things to think about. The electrons, if these are the three things that'll help us in the next, this coming slide. If you had a PN junction, we put an electron here in the depletion region, it would get swept off. Second thing is we're biasing, we're putting certain voltages across this transistor, making the base more higher voltage than the emitter, making it forward biased, and we're making the collector base junction reverse bias. And finally, we're remembering that the current that would flow in that case across a PN junction, the forward bias operation, is dependent on the doping concentrations. So coming back to our bipolar transistor. So we're redrawing it here instead of the schematic, we're showing the NPN. So this is the base. This is the emitter. And this is the collector. We're talking about exactly the same voltages that we had here, except instead of the schematic drawing, I got the sort of the semiconductor cartoon drawing of it. Okay, so base emitter collector, and we have the base emitter junction. We're forward biased, so this junction here is forward bias between this P and an N, because the base voltage is higher than the emitter voltage by 0.8. And then we have this junction being reverse bias because the collector emitter voltage is 1 volt and the base emitter voltage is 0.8. That makes the collector base voltage 0.2 volts. So means that this PN junction is reverse bias. Okay, so now this is forward bias. If this junction is forward bias, what happens? Well, you're going to get this current flowing from this. You're taking away from this depletion region, and you're allowing diffusion current to flow, basically electrons to flow from a place of high electron concentration, which is the emitter, to a place of low electron concentration, which is the base region. So you're allowing that to flow. And then you're allowing holes to flow from a region of high hole concentration to a region of low hole concentration. So from base to emitter. Now, if you have a lot higher doping on the emitter side than the base side, then the amount of electron current is going to be a lot higher than, can be a lot higher than the hole current. Okay, so N plus, so we said, N means that we have donor dopants in that region. So donor dopants, so N sub D dopants. And shorthand for a region with a very high number of donor dopants is N plus. Okay, you also have like N plus plus means even like higher. It's a relative shorthand notation. It just basically means very high concentration of N sub D on that N side. Okay, and then when you don't have a plus in front of the N or the P, it means, not such a high concentration. In this case of acceptors. Okay, so when we draw something like N plus P, means this guy's doping concentration is much higher than the base's doping concentration. So basically this implies that N sub D is much higher than N sub A, calling it N plus and P. Okay, again, it means that you have, for say every hole going across here, you might have 100 times more electrons going this way, or 1,000 times more electrons going this way. Okay, so that's this PN junction. So as far as we're concerned, so far so good. This is just acting like a forward biased PN junction. So how's the collector come into this? Well, the collector is connected so that it is reverse bias. So there's a depletion region on the collector side. Okay, so now we'll talk about the reason why you cannot look at this as two back-to-back diodes. So this is why this is not the case. It's because, it's because this base region is very, very small. So the base width means the actual size of the base might be, 1 times 10 to the minus 7 meters. So we're talking about there's a very small distance between this junction and this junction. Okay, physically a very, very small distance. That means that these electrons, as they go into the base, they are so physically close to this depletion region that the majority of them just get pulled into the depletion region. Okay, so they go straight from the emitter to the base, and they cross the base because the base is so thin. It's incredibly thin. And they end up in this junction. And as soon as the electrons end up in this junction, like we talked about here, in this case, as soon as the electrons end up in this junction, they get swept into the collector. So basically the electrons leave the emitter, a really large number of electrons, as leave the emitter, they get pulled into this depletion region and then get pulled into the collector. So in effect, so basically you get almost all the electrons make it from the emitter to the collector. They just shoot across the base. So effectively, what this looks like is you have a situation where, if you just want to think about currents, you have a situation where you've put in a small current from this node. So I can think of it as I'm putting in a small current here. It's in the form of holes, but it's a very small number. Okay, so let's call it I sub B, the current going into the base. So let's say I sub B is 1, I don't know, 1 microamp. Micro is 1 times 10 to the minus 6. Okay, 1 microamp going in there. So you've got a situation where you have a small current going in here, and you might be generating a current of 100 microamps at the collector. Okay, so you put a small current into this control node. You can think of this base as the controlling element. So by putting a small current here, you can get a very large current at the collector. And then, if I sub B is 2 microamps, this collector would be 200 microamps, and so on. So you've created a situation where this point is not directly connected to either one of these points, but it can control the current through these points. Okay, so another way of looking at this transistor is that this voltage from base to emitter, although it's not connected to this collector, so this voltage is controlling the current going into the collector. So this device is acting like our voltage controlled current source. So there's a voltage coming in here, and it's this voltage. So let's say this is, in this case, this would be the base. This would be the emitter. This would be the collector. So although this voltage is not directly controlled, is not directly connected to the collector, this voltage is actually creating this large current flowing into the collector. Okay, so this is how it works. Basically, by once you forward bias the base emitter voltage, you get a bunch of current going in here from the emitter to the base. So one important thing about a bipolar transistor is the emitter is doped a lot higher than the base to get this asymmetry in the currents. And the second thing that's important in a bipolar transistor is the base width has to be small enough that all this current gets swept into the collector, or the majority of it. Okay, so those two things allow you to get this voltage controlled current source action that we'll talk about in the a little bit more in the next lecture. It's 6:45 now. Brandon, sorry, I didn't see your notes. So you said to add gain we include R times I. Can you say that again? Or which slide was this about? Brandon, you might be muted.
Oh, sorry. Can you hear me now?
Yeah, I can hear.
Oh, sorry. I wanted to say real quick before we get to that.
Huh?
You said the two main points were for the emitter, it's doped much higher than the base. And then what was the other main point?
Is that the base width, the physical width of the base has to be so short that these electrons get swept, just go straight through the base and end up in the collector.
Gotcha. Okay. And then for the question I had earlier, it was on, let's see, the slide labeled exponential voltage dependent current source.
Yeah.
I believe it's slide 5. Yeah.
Yeah.
Yeah, this one. So when you wrote in RL and V out, you mentioned just something about that's how we get gain, or I don't know, that I just got lost at that point.
Sure.
What you said adding RL does.
Yeah. So if you don't add RL, you just end up with a current coming out of this node. Okay. But you want a voltage gain. So to get a voltage gain, you have to transform that signal from a current to a voltage. And an easy way to do that is just putting a resistor here. So you go from this current, you multiply that current by this resistor to get an output voltage. So that's all I was saying. So here, for example, like you basically want a situation like this where V out is R sub L times this KV1. So you have to put a resistor here as well. That's, yeah. Any other questions, guys?
Could you scroll back down to the last slide?
Sure.
For a second. Yeah, okay, thank you.
Sure. Okay, guys, and unfortunately, I'll put in some more homework for you guys, homework problems to solve now on chapter 3 as well. So you can start playing around with this. Okay, guys, if there are no other questions, I'll let you guys go and I'll talk to you guys on Thursday. Take care.
Professor?
Yes.
Did you get my last email concerning about the test?
Yeah, I think so.
Okay, good. Just wanted to make sure because you did say that if we didn't put everything on the paper, we were supposed to fix it and resubmit it. So I just wanted to let you know about that.
Okay, sounds good.
Okay.
Okay, thanks. All right, guys. Have a good one.
You too.